Speech!
Welcome, everyone. My name is Darcy. I'm one of the organizers here with Taste of Science. Taste of Science, if you're not familiar with us, is a national event series with several chapters around the United States. Currently, we have 7 active city chapters as well as an online chapter. Our mission is pretty simple. It's to make science more accessible to everyone through public events and activities. So Taste of Science is one of our projects under the nonprofit Scientists, Inc. You may be familiar with a few of our other projects, Sensational Sci-Fest, which is a science festival designed for kids with sensory sensitivities. On that note, if there are any neurodivergent folks in this room, we have fidgets in the back, and we have disposable earplugs available during the game time. Another project we have is our Webby-nominated podcast, Two Scientists. Additionally, we are completely volunteer run, so we do thank you for buying tickets as these funds go straight back into our programming. If you are interested in getting involved, we have a volunteer sign-up sheet in the other room. You can visit our website also at tasteofscience.org. All right, well, I am excited to introduce our speaker for this evening, Dr. Joel Brown, who prefers to go by Joel. He's a faculty member in the Department of Integrated Mathematical Oncology at the Moffitt Cancer Center. Joel is an evolutionary ecologist who studies nature and cancer through adaptations of the organisms. For over 30 years as a wildlife biologist, he has worked from A to Z, including aardvarks in South Africa and zebras in zoos. His personal favorites are squirrels. He currently applies principles of ecology and evolution to understand and treat cancer. We have included some sign-up sheets for the games, if you don't mind, filling them out and just passing them along to the other tables. And with that,
Great, thanks. Can this clip on? Well, thank you all very, very much. It's so wonderful to have you folks here. Saw A Beautiful Mind movie. I did have a chance to meet John Nash many, many years ago. Yes, as a game theorist, you bet. And you probably discovered any of us that are game theorists, we're nuts. I'm going to come see you afterwards. Yeah, there's a counseling psychologist back there that can go through things and it's fun to see some friendly faces in the audience. Yes, thank you guys for coming and looking forward to making new friends in the process. So much of my career has been a wildlife ecologist, and basically my career has been one of spending time in the field studying wildlife, and then being at my desk being a math nerd. And so those are generally seen as what is called mud and boots ecology, and then the other one is being a biomathematician. And so by trying to do both, you will probably discover I'm worthless at either on there. But for me, it gave me great joy. And in fact, it paid a dividend I never anticipated, and that is usually one in the field. I was at the University of Illinois at Chicago for 30 years in the biology department as a faculty member. And usually, in a research institution, you're supposed to stick an animal and, pick an animal and stick with it. Pick a plant, pick a microbe, pick something and stick with it. No, in fact, in my lab, it was always my grad students and my friends that picked my study organism. So all the critters you see up there, those were picked by various grad students and whatnot. So it became very frequent in my lab that we worked on just about anything. Everything from octopus in Prince William Sound, to lions in the Serengeti, to Patagonian cavies in Argentina, coral reef fish, even soybeans. How's that for bizarre on there? But as a consequence, and it turned out to be something I did not anticipate when you work like that, it was about in 2008 that Bob Gatenby, he's a physician at Moffitt, kind of our thought leader in some of the stuff we do, and then Tom Vincent, he'll pop up briefly, who was my game theory mentor at the University of Arizona when I was getting my PhD. I was offered a new study organism, a really boring study organism, but a study organism that's to die for nonetheless, and that was cancer. And then I'll explain how eventually, as we get to the end, how did I wind up then being among these wonderful people, some of the folks that work at Moffitt and whatnot, which has been a real privilege. So what is game theory? And generally, the way I like to define, there's a number of definitions of game theory, a field of mathematics. I like to think of game theory, the easiest way to define it is that when your best behavior depends upon the behavior of others. How many of you ever felt like, crap, I don't ever think I can do the right thing. I always seem to be doing the wrong thing. But just think about it. It may not be you, it may be them, right? But the whole point, though, in game theory is this idea that it deals with how do you determine what is the best thing to do when that is determined by what others are doing. And so game theory can be quite expansive. Obviously, games have been played ever since there were humans. Actually, bacteria plays games. Plants play games. Games are all around us, these types of situations. But the actual formalism, somebody who's actually willing to kind of write it down and turn it into a mathematical field, is relatively young. And it was these two Hungarians, von Neumann and Morgenstern. I know they sound like Guildenstern and Morgenstern out of, sort of Hamlet. But these two guys then actually wrote it down in 1944. So it's a relatively new field. And then a beautiful mind, there's John Nash. He became famous because, as we're going to see in a moment, there's all sorts of different sort of solution concepts. What should you do? How should you behave? And then John Nash will talk about it, came up with what is probably the most enduring solution in game theory, which is called the no regret strategy. Although you're going to discover you can often regret that we're at a no regret strategy. But at a no regret strategy, you can't do much about it. And then these two fellows, John Maynard Smith and George Price, in 1973, actually came up with what is evolutionary game theory, this realization then that nature plays games. In fact, that almost any of the adaptations of organisms, many of the adaptations of organisms are in response to the adaptations of other organisms, if you can imagine that. Think of a hummingbird and flowers, bees and flowers. We'll talk about some of them. And then I had the privilege of having Tom Vincent, who is in aerospace mechanical engineering. And his specialty was pursuit evasion games. In fact, part of the reason why some of these Iranian missiles are pretty good, back in the mid-70s, he trained the Iranian PhD students during the time of the Shah to be able to write the algorithms for smart weaponry. Was part. But his love, he was a wonderful, wonderful human being. He died of cancer in 2009, but his love was nature and evolutionary games. And so I had the opportunity at the University of Arizona to start working with him as a grad student. He was my co-advisor and was able then to continue working with him right up until his death. So what do games have? It's pretty simple. You're going to be playing some of these. There's players, you guys, the organisms. There tends to be some sort of rules, something about the environment or the situation in which you take your strategies. You have choices. You have choices, or they can be heritable choices in the case of organisms. You have choices, and those choices, given the rules and what the other players do, result in payoffs. And the payoffs can be quite diverse. So what do these games look like? Well, right now, this is probably Donald Trump's favorite game. There's that. And so if you're a big fan of Donald Trump, you're neutral or not, the fact is this is his favorite game, which is the game of chicken. And the game of chicken, in the way it's formulated here, you can choose to be aggressive or non-aggressive. And that there's a payoff. We'll just call it B, a benefit. And this benefit can be divided up. The way you read these matrix games, sorry, this gets really nerdy, please bear with me, is your opponent is the columns, okay? Your opponent picks the columns, you pick the row. Are you with me? So the very essence of game theory, and it gets great. How many of you have ever gotten into situations of infinite regress? Well, if I do this, they're going to do that, and then I better do this, but maybe they know I'm going to do this, so then how many of you have ever seen Princess Bride and the Battle of Wits? Is that kind of infinite regress. And because what happens in game theory is they're you. So you're you, and you pick the row. And if I'm playing a game with you, I'm the columns, right? But to me, I'm me and you're the opponent, right? So game theory is all about reference. You, identifying as you, and then the others. But the others, of course, they themselves are themselves relative to you. Does that make any kind of sense? So at any rate, so in this particular game, your opponent would pick the columns, you would pick the rows. And what you notice here is that if both play non-aggressive, if both are non-aggressive, they split the benefit. Is that going to make sense? But let's say you're non-aggressive and your opponent is aggressive. Then you get nothing. Now imagine that you're aggressive and your opponent is non-aggressive. You get the whole benefit. Do you sort of get the idea here? But here's the kicker, and this is what's kind of going on in the nation right now, is that if both are aggressive, they split the benefit. That's kind of cool, but there's a cost. So an example of this is kids. Part of my growing up was in Zimbabwe, and my dad was working in a mission hospital. I don't know, I was like 10 years old. My sister and I decided we were going to play chicken. Actually, we were going to joust on our bicycles. That meant getting on our bicycles, taking broomsticks, and heading towards each other with broomsticks. Now, in this particular case is a good example of the cost. Neither of us swerved. We stuck with it. And basically her broom went right into my stomach, lifted me off the bicycle, planted me on the ground, and knocked the wind out of me. Meanwhile, my broom went into her front spokes, and the whole front tire just collapsed, and she face planted in front. We both concluded we're not going to play that game again, and it would make up, speaking of a game within a game, we would make up a story to our parents to explain, because we were not going to admit that we got there, that somehow the bike just broke on that. So the notion then is if both are aggressive, there's a cost. So one of the things that's clear here is that from a collective, what's the best thing for the world? Non-aggressive. You just split the benefit, right? But if everybody is non-aggressive, what's your best strategy? Be aggressive. And so this game, you can use it to answer the question, why is there evil in the world? You know, if people are so inherently good, why is there evil? Well, the game of chicken sort of explains that, because what happens then is non-aggressive, everybody being non-aggressive is never stable. Can you see that? It's never stable, because if you have a world where everybody's non-aggressive, then it really pays to be aggressive. Now, what's worse in this game is it turns out how big the cost is determines whether you wind up with a mixture. If the cost is very high, as in the case of my sister, you tend to get good behavior. There will always be some. It'll be a mixed strategy. An individual may sometimes be aggressive. Sometimes they'll be non-aggressive. You get a mixture. But if the cost is small enough, you can wind up with a world where everybody's aggressive. And Donald Trump is a genius at that. What he has done in his social media and whatnot, he's lowered the cost of being mean. He's basically made it acceptable. There isn't a penalty for being aggressive. In fact, he celebrates aggressiveness. And so what has happened is not that Americans are any different. It's not that we've changed. We are who we are. But sadly, well, depending upon what you like in the world, I won't make, you guys can make your own normative judgment. But what's happened is C has become smaller and smaller and smaller. And this has encouraged, among the same people, more and more aggressive behavior. So the context is everything. How's that for scary? We can be the same wonderful human beings. And the structure of this game can determine what happens. Another game I'm sure you're all familiar with is, how many of you have ever been in a situation where you just have had to do the work? That old saying that if I don't do it, gosh, look at you guys. If I don't do it, nobody will do it, right? I guess if you want it done, you're going to have to do it yourself, right? How many of you have been in that situation? All of us? Very good. So in that case, you guys are producers. How many of you have ever freeloaded? I'm so glad somebody's doing all that work. I'm just going to kick up my feet on the couch and just relax and have a beer. And that's called freeloading. How many of you have ever freeloaded? That have sort of, and now, so one of them, a classic producer-scrounger game, and there's many of them, is this idea that if individuals contribute, there's a benefit. It's called a public good. In this case now, it's a public good. So if somebody contributes, if somebody does the work, there will be a benefit, and both individuals get the benefit. How's that for cool? But also, many hands make short work. That kind of makes sense? So what happens then is if both individuals free ride, well then nothing happens. If you free ride and the other person does all the work, you get the benefit. Remember, you're the rows, they're the columns. Now, if you contribute and the other free rides, you get the benefit as well because it's a public good, it's a public benefit, but you pay the entire cost. Does that make sense? And then if both individuals contribute, oh, that's great. You know, you split the cost and you get a benefit. Now, what's interesting in this particular game is even if both contributing, so let's say C over 2 is less than the benefit. So imagine up here is positive, right? If up here is positive, what's really scary, of course, then is both contributing is the way to go, right? Because if nobody contributes, you're down here at 0. But if the cost is greater than the benefit, nothing will happen. Free riding, even if both contributing would be a better world, you can wind up with a situation where nothing happens. And so this you often see in certain situations. You go into a situation and say, you know what, if you guys just, you know, did a little bit of work collectively, you could be better. But if the cost is too high, without a collective decision, without kind of a collective decision, and what's worse is even if B is much greater than C, you always wind up with a mixture of contributors and free riders. So if each of you has in your life been a free rider and a contributor, congratulations. You do game theory, and that is the solution. And then, of course, there's the classic game that teachers experience in high school, and that's the prisoner's dilemma. And that's where you caught somebody cheating. You caught these two cheaters. They, of course, tell you, we've never cheated in our life. We don't cheat, we don't cheat, we don't cheat. And if they did, it's the very first time, so be nice. I'm sure you've heard those tales of woes from cheaters. And so the idea then is you try to, of course, separate them. And then you say, look, if you fess up, I'll let you off easy. And then the other person's kind of screwed. But basically, the prisoner's dilemma can be one of cooperation, non-cooperation. And here you can sort of see, notice all of these structures have benefits and costs, but slightly different cost structures. So if there's no cooperation, we just have 0. And the idea is that you bestow a benefit. So in this game, if you cooperate, you give a benefit to somebody. You don't get it. It's the opposite of the public good. You don't get it, but you incur a cost. And so what happens then, if I cooperate and I'm up against a non-cooperator, I pay the cost, but I get no benefit. Can you see it? And then, of course, if both cooperate, that's great. You get the benefit. That person gives you a benefit. They pay a cost. I get a benefit. I pay a cost, B minus C. But if I'm a non-cooperating and the other person cooperates, that's great. I don't pay any cost, and I get the full benefit. You can sort of see the structure here. Now, the problem with this game, and why that, well, not the problem with the game, but what makes this game central to what's called the dilemma of altruism, the dilemma of cooperative behavior. Why is it we are cooperative? Is because clearly, if everybody is cooperative, what's your best response? If everybody's cooperative, so that's the column, what is your best thing to do? No cooperation. And then if everybody is non-cooperative, is there any benefit to being cooperative? If everybody is non-cooperative, no, there's no point. And so this is why this game is kind of the classic dilemma of how you get cooperation. Well, it turns out there's 2 ways you can get cooperation. And that is, have you ever heard then that blood runs thicker than water? So one is relatives. Be nice to relatives. And it turns out, I won't go through the math, but it's called kin selection. If your level of relatedness to somebody is greater than C over B, so put it in your calculator, figure out how related you are to Viral, and then calculate kind of the cost and benefit of doing something nice for him, even though it kind of costs you. And then you can say, okay, that's great. We're related by X over there, and if that's greater than C over B, be nice to Viral. That'd be great. Otherwise, the other is what's called reciprocal altruism. Oh, do you? Okay, are you beginning to understand something? Yeah, you can. Hopefully there's a little bit of self-help here for you in your that. So the other, of course, is reciprocal altruism. If the game is played again and again, then what it is you can then punish non-cooperators or reward cooperators. And so that's referred to as I'll scratch your back if you scratch my back. Does that kind of make sense? And it turns out that if K, it's called the coefficient of reciprocity, if K is the likelihood that somebody at some point will reciprocate a kindness, is greater than C over B, you also get cooperation. And so that's why you often hear in psychology that just being nice to somebody can make them nicer to somebody down the line. Have you ever heard that pass it on? You do a goodness to somebody and pass it on. Actually, that K, you can calculate it, the likelihood of it being passed on. Does that kind of make sense? So now we're going to kind of go into more games. Do these make sense? Any questions at this point? Okay, so now, here's a really exciting game. I know, thank you. Thank you. Yeah, this is one that's just going to stick in your head. It's much better than any of these games. Look at that. It doesn't have a flashy cover or whatnot. But remember, who is your opponent? The rows or the columns? Columns. Who are you? Okay, so I want you to examine this game for a little bit. Take a little bit of time. I'm going to take a sip of water here. Look at all those funny numbers. And I want you to be thinking in your head, what would you play? What would you play? Now remember, your opponent is picking the column. You're picking the row. Over here we have a PhD in counseling psychologist. I'm sure he can see all sorts of...
Way steps ahead.
that...
I won't give the answer.
So go ahead and think about what you would play, and in your mind think why. What you would play and why. And I'm going to give you guys a funny hint. In game theory, every one of these, this is why this really boring tutorial game is up there, every one of those strategy can be a rational solution to the game. Every one of those, A, B, C, and D, there is a rationality. And that's the other part about game theory. One of the horrible things about game theory, and I think the wonderful things about game theory finds the rational in what otherwise seems irrational. Okay, how many people in here would play A? Cool. Why?
Because if I pick B or C, there is the possibility that the opponent choose a column that gives me 1, so I don't want that. Same for the D. We have 7 that is higher, but on average, I have more probability of having a higher number with row A.
I love it. Isn't that great? You're already hearing the logic in game theory. Wow, that was like brilliant. Okay, how about you?
Well, I would have to like sort of understand my opponent, but
No, you don't know what your opponent's going to do. You have to just, right, but you're trying to imagine.
B is sort of the most effective value, sort of like row that my opponent can pick. It's like the highest.
Okay.
Possible.
So we're going to get to those. We're going to find out who would have played B. So what you're saying is, which is great, here is the infinite regress. You're saying, aha, people are going to play B, so I'm going to play A, without thinking about, well, maybe all the Bs are thinking the same thing, and so they're going to decide to play A. But what is an A? And you guys nailed it. It is called the max-min. It's often referred to as the pessimist strategy. I don't know what my opponent's going to do, but I'm sure it's going to screw me.
Yeah, exactly.
I don't know what my opponent's going to do, but I'm sure I'm going to wind up screwed.
Yeah.
Yep, and so therefore you look at here and you find, so the max-min strategy is you find the strategy that has the highest minimum on the row. How's that for wild?
Yeah.
You find the highest row minimum. You find the highest row minimum and you go for it. That's great. Who in here would pick B? Anybody? Nobody would pick B. Because anybody that picks B, boy, that's who I want to have as a partner on a deserted island. On there. So B is really interesting. B is what, here you guys go. B is referred to as the group optimum. B is the group optimum. If everybody plays A, what do you get? Everybody plays C, what do you get? If everybody plays C. Everybody plays D. 4. If everybody plays B, wow, not a single soul picked it. Wow, you guys are human. Yeah, not quite perfect, not quite altruistic, but yeah, so B is considered the group optimum. That is the one that maximizes the collective payout. Those are the people I want to be with. How do you find the group optimum? You look for the highest diagonal. Did you see that? You look for the highest diagonal on there. Okay, so how many people would pick C? Cool, okay, so I'm going to go with you. So why did you pick C?
It's the highest average.
What's that?
It's the highest average.
I love that. Hold that thought. Why did you pick C? Same? Same?
It has the 11.
It's the 11. Okay, so those are, so C. Yeah. So, yeah, way to go. Yeah. So C actually has two properties. So C has two properties. You guys got it. It is the largest average if you sum up the row and divide it by 4. So if you say, look, I don't know what my opponent's going to do, I'm just assuming they're random. If you're assuming that your opponent's going to play randomly, then C maximizes your expected payoff. So that is one of the aspects. So it maximizes the average row sum. How's that? Aren't you glad there's not going to be a quiz afterwards on there? And then, oh, thank you, Kevin. That's the optimist strategy, the opposite of you. Are you? Yeah, so Kevin is the, are you feeling lucky? Oh yeah, I don't know what's going to happen today. Yeah, okay, I don't know what's going to happen today, but it's going to be great. Everybody's going to be great, and that's 11. Okay, how many people picked? Okay, you think so? Yeah. So he's not wise. He hasn't become jaded. Yeah, he hasn't been stomped on in life yet. Yeah, that may it never happen, Kevin. Please.
Everybody will pick B, and some people will pick C, right? And
Yeah.
everybody's happy.
Okay, there you go. Except the people that pick B when they play you. Yeah, look at the poor people that pick B and then you pick C.
Exactly.
Those poor B people are really kind of, yeah, sorry, Kevin. Yeah, that. Okay, how many people would pick D? Anybody? Oh, yeah, I'm glad somebody did. Otherwise, I'd have to explain a vacant strategy on there. Okay, why?
I was going for the maximus strategy, but I did it wrong.
Yeah, that happens a lot too. How many of you have been in a situation where I didn't really mean to do that? I didn't understand. Yeah, I didn't really understand what was going on. Can I play over again? Can we turn the clock back and play over? So D has a number of interesting properties. Anybody else want to comment on D? D actually has two interesting properties.
Please.
No, go ahead, and then we'll bounce. Yeah, that.
So actually, in terms of probability, so I'm not in mathematical department, so please have mercy on me. But so maybe looking better at D, if you remove 2, actually it has higher probabilities of picking a higher number compared to A. It's just that if I have to take into consideration the 4 columns, it's better A. But if I remove 2, it's better B.
I think you should become a game theorist. I love it. I love you. I love how you approach it. Go ahead. What did you see in D?
Oh, it's the worst for everyone else.
Yes. Oh, yeah. That's a screw my opponent strategy. Screw my opponent. Oh, yeah. Well, suddenly you just woke up. Yeah, isn't that great? Yeah, it's like, whoa, I didn't see that. Yeah, it has the lowest average column sum. I don't know what my opponent's going to do to me, but I'm going to make sure they don't do well. I'm going to make sure they don't do well.
I don't want to lose with my...
That is, again, a Trump strategy. Yeah, actually, if you notice a lot of his strategy, again, better for worse, just not, is the idea of what will inflict the most. Sort of a bully strategy. Does that kind of make sense? But D has another property, and I couldn't help but put it up there. I snuck it in there. You can't quite see. Does anybody else see? Viral, did you see? D has another really important... Yeah, it's got kind of a low spread, but that's not it. But it's got something. You could have won a Nobel Prize for this. Yeah, this would have gotten you a Nobel Prize.
You never lose someone?
No. And that's okay. You're not expecting to get a Nobel Prize in 3 minutes of game theory. Although, the number of Nobel Prizes in economics that go to game theorists is going up and up and up. Yeah, last year's Nobel Prize in economics was game theory. So most of the Nobel Prizes in economics in the last 20 years have been to game theorists. Okay, so what is interesting is D is the Nash equilibrium of the beautiful mind. Of course you all saw it. It's the Nash equilibrium. It is the Nash equilibrium. And remember, a Nash equilibrium is what's called a no-regret strategy. It says that if everybody's doing it, that's what you want to do. You have no regret. So let's play it out. If everybody plays A, if I tell you everybody's playing A, what would you like to play? B. So clearly A is not a no-regret strategy. Do you see that? Okay, everybody's playing B. What do you hope you play? Haha, it's Kevin.
D.
If everybody's playing B, you want to play C, right?
Yeah.
If everybody's playing C, what do you want to play?
D.
D, right? Can you guys see it?
Yeah.
Now everybody's playing D. What do you want to play?
2 times you play D, you win.
Do you see if everybody's playing D, what do you want to play?
D.
D.
Half of the times if you play D, you win.
Yeah, well, no, you always, I mean, you get 4, and if everybody's playing D, that's the best you can do. That's the best. So therefore, that's called a no regret strategy. And so there's a couple of interesting things about no regret strategies. They're phenomenally stable. Now, in this case, is it the best outcome for the group? No. In fact, everybody would be better off playing B or C, right? Everybody would be better off playing B or C. B, of course, is what everybody should be doing. But what you notice, to get to B requires a collective change. You've got to go around and convince everybody that D sucks. We can do better. We need to organize, right? And of course, people that are in power, look at what happened in Iran when the people tried to organize. What does Donald Trump do when people try to organize against right? And so what's interesting then is B is something that can be achieved, but it requires collective action, collective trust, and you can't include Kevin. So
I always was wanting.
that's right. So as everybody sort of see a bit of the essence of game theory, and you can start to see, are you guys beginning to at least feel some of, I know this is a really boring game. I'm doing this, Christina and Darcy, because those games will seem so much better. They're pretty, they've got cool things, whatnot. And when you screw your neighbor in those games, it seems like you're being nice in a funny sort of way. But did everybody see this? Okay, so now we're going to run through some games in nature. And then we'll get to cancer, and then I'm going to spin back to humans. Okay, we're going to just end again kind of on humans. So I'm going to ask a very Zen question. Why is there wood? How many people in here like wood? Yeah, just glad there's wood.
I'm super happy there's wood.
Yeah, are you happy there's wood? I mean, like me, I love squirrels. And tree squirrels, gee, what would tree squirrels do without wood? Clearly that's why there's wood out there. And that's actually my house in Idaho. We have a funny geodesic dome house in Idaho. What do you guys think? Does that look like fun? Just came from there a few days ago in there. So how many people like to do woodwork? Cool. How many people like wood carvings? Find wood carvings kind of appealing and whatnot. Sure. Okay, so now we're going to get to it is, why is there wood? Why does wood exist?
The evolutionary development of plants.
Okay, yeah, that's kind of a, I mean, that's a statement of fact. Still doesn't tell me why or what. I'm going to hold on to that. I'm going to go back to that person there. Why is there wood? Yeah.
Did I piggyback on the evolutionary?
Well, yes, wood evolved, of course. Yes, we know wood evolved. If it didn't evolve, it wouldn't be the Carboniferous. Now, hold on a second. We'll get over to you in just a moment. I'm going to go to that gentleman.
Secure one.
I know, it kind of sounds like a Zen. Doesn't it kind of sound like a Zen? Yeah, but for what? If it's evolutionary, it's an adaptation. So as an adaptation, it has a purpose.
It's kind of like a defense mechanism.
It's competing for something.
Okay, so you might say protect the cells, but actually all that wood just provides other ways for insects and woodpeckers and whatnot to go at it.
I mean, it's a transportation system.
Okay, it is. And of course, cavitation and trying to get stuff from the roots up to the top and down again. Think of a redwood. That's hardly an advantage of wood. It's a royal pain. You got to pump the stuff all the way up and down. Do you have a thought?
Still going with protecting the cells.
Okay, protecting the cells.
There was too much carbon during the carbonic period in the soil, so we had to use enough weight.
Oh, well, that was nice. The tree said we need the Carboniferous
Yeah,
so that we can have burn, baby, burn. Yeah, oh yeah, I see it. Yeah, I get it. You guys are like there. Okay, your turn. Go for
I
it.
think it's just random. Just a
Oh no, I assure you that tree is not random. The height, that 30 meters of beech tree is not random. But no, good. That's
To give structure.
a structure, but why? I mean, do I just want to be a tree?
Yes.
That's my essence. That's my totem. I'm basically a dryad. I love it. Animism gone wild. If we didn't have trees, we would...
They had to keep getting taller to get access to sunlight.
Yes!
You have to outcompete the other plants.
Yes! The whole reason there's wood. Thank you, I know, that was the whole reason for wood. Yes, I know, isn't that great? Yeah, I love it. Yeah, No, it is entirely a game. It's a game of competing for light. It's a game of compete. It's all about competition for light. If all those trees could agree to be half the height, just think how much more seeds they could produce. Just think how much more. So for instance, a mighty oak in Chicago, and I've studied oaks and squirrels on there, one oak tree, the average production of acorns from a single oak tree is the equivalent grain crop of 4 corn stalks in Iowa. So it seems like the oaks are doing everything but producing babies. That. Why? Because what they do is they overproduce roots so that their neighbors don't get the nutrients. That's called a tragedy of the commons. How's that for rude? They will overshade things. Think about a dark forest. Anybody who's come from upstate New York knows that in the middle of the summertime, when you go into the dark woods, 2 things happen. One, it's really dark, and the mosquitoes are vicious inside there. And then the other is at height. So this is one of this called an evolutionary arms race. How tall do you need to be?
Well, you
guys are overthinking this guy.
Minimize the resource costs that you get from the soil while maximizing your height above the other trees.
Yeah.
Taller than the other?
Yeah.
Exactly. All you have to do is be taller than your neighbor. So there's a way of solving this. We even published a paper on this. Isn't that fun? You can actually get a paper published just pointing out. So really, you just need to be taller than your neighbor. But then your neighbor is taller than you. Well, then you got to be taller. So it becomes a game of poker. You keep upping the ante. And then you say, okay, there's that beech tree. If I'm 5 meters, okay, I want to be 6 meters. If you're 10 meters, I want to be 11 meters and whatnot. And then you hit 30 meters at that point. And there you are. And you say, do you want to be 31 meters? No, the cost of blowing over, tornadoes, the expense of moving nutrients, it just isn't worth it. So what's really cool about height in trees is there's a couple of observations. One is the height of forests around the world, and we won't have time, you can ask me later, why are the tallest trees in the world in California? It doesn't make sense. It's the environment. So a different environment, there's different costs and benefits to being tall. Different costs and benefits. And the other cool part then is it means that regardless of what forest it is, within a forest, it can be a tropical rainforest that has 80 species of trees in a single hectare. Or it can be up there in the boreal forest where there's a whole whopping 3 species in a hectare. The canopy within a forest in old growth will always be equal. Isn't that cool? Nobody will stick up and nobody will stick down, because to stick up is too costly, because if it was worthwhile, everybody would do it. And there's no point in being 2 meters shorter, you're still in the shade. And so that is how they determine, when you read about how much of the rainforest is being cut down per year, and you wonder, how do they do it? That's kind of cool. I'd like to get hired to go to Indonesia, go to Brazil, go to the Pantanal, go to Manaus in Peru, and check it out. The way they do it is satellite imagery. And if the trees are all cockeyed, there's been cutting. It's not old growth. If it's as flat as a pancake on top, how's that for cool? Game theory is used to actually see where the forests are. Does that kind of make sense? My favorite games, this really says something horrible about me, much of my career has been predator-prey games. A couple observations about predator-prey games. Whether you like predator-prey, how many of you agree it is dramatic? Yes, it is dramatic. Usually it's more fun to be the predator than the prey, which is kind of too bad. Okay, so first I want to get a sense of where you guys come out on this. I know I'm kind of running over time. Can I keep going? Or are you guys, is this, okay, yeah. So if I'm kind of boring you guys. Anyway, so I want you guys, how many of you have watched nature shows? And there's like the Serengeti. Have you guys seen those shows on the Serengeti? And you always have that funny voice. You have to have that kind of Attenborough voice or whatnot. And here we are on the Serengeti, watching the golden globe of the sun rise on a new day. And we see in the distance a gazelle. And she's a mother with a young gazelle trying to feed her youngster. And then over there we see a cheetah. We have a cheetah mom. She too is hungry. The cheetah spots the gazelle. The cheetah mother, to be a good mother, begins crouching, stealthily moving silently through the grass, unobserved to the gazelle. And then suddenly, in a burst of speed, the gazelle explodes out of the vegetation. The mother gazelle suddenly, with reflexes as fast as lightning, begins to flee. And the chase begins between the fastest animal on earth and a gazelle, which is almost as fast. Okay, so how many of you sort of watch those kind of shows and whatnot? Okay, so this is, you can look around. How many people are rooting for the cheetah? Go ahead and admit, yeah, rooting for the cheetah. You want the ending to say, where it's like, and how many are hoping the gazelle gets away? Yeah, now obviously this game has to have different outcomes, because if the cheetahs always won, there would be no gazelles. And if the gazelles always won, guess what? There'd be no cheetahs, right? So predator-prey games. Now predator-prey games can be kind of interesting, and one of the ones so much of my career, and it's referred to as, isn't this great, I got to found a field, it's called the ecology of fear. Isn't that great? The ecology of fear, and that is in these systems, actually the game between predator and prey is played out more in the non-lethal, the things that prey do to keep from getting eaten, and the things that predators do to try to get an edge. Often that has bigger effects in the ecosystem than the actual killing. That's the whole point of terrorism, right? Is the point of terrorism to try to eliminate everybody? What's the goal of terrorism? To change the behavior of those that don't die, right? The whole thing is to instill fear, right? Okay, so we're going to take a look at one of the games I had a chance to research on. And aren't they cute? Those are gerbils. They live in the sand dunes of the Middle East. They live in the sand dunes, and then they're preyed upon by owls. Barn owls eat them. And then down there is a horned viper. So this is pretty typical deserts around the world. You'll have desert rodents, and you'll have owls, and you'll have snakes. So any of you have taken ecology, owls eat gerbils, snakes eat gerbils. What's the relationship between owls and snakes? What would we call that if you're teaching ecology? What's the relationship between the owls and the snakes? What's that? Well, they're both predators of gerbils, but what would you say about them? They're competing predators, you bet. The owls are eating gerbils that the snakes would like to eat, and the snakes are eating gerbils that the owls would like to eat. Guess what? It's not that simple. Isn't that cool? Because imagine the desert where you have big picture sand dunes with islands of shrubbery. Can you guys see it? Picture islands of shrubbery and sand. And think about it. If you're a clever gerbil and you know there's owls out there, where would you go to hide?
Just like borrow something.
Well, let's say you're not quite ready to go to your burrow. You're still going through the sand looking for seeds.
Just like go inside the plants.
Yeah, go into the bush. Go into the bush, absolutely. If you're going to try to escape owls, being in the bush is a great place to be. Now imagine you're a clever snake, and you know that clever gerbils escape owls by going into the bush. What should you do?
You hide in the bush.
You hide in the bush, right? Wow. And in fact, this game goes on every night in those sand dunes. Basically, it turns out that the owls actually frighten the gerbils into the fangs of the snakes, and the snakes return the favor by frightening the gerbils into the talons of the owls. How's that for rude? How's that? So basically, owls make it easier for snakes to kill gerbils. Snakes make it easier for owls to kill gerbils, which is why just about every desert in the world has owls and snakes. And in just about every desert in the world, that's what owls and snakes do. And it was so fun doing the research because we got to play around with what happens if you remove the owls, have the snakes and whatnot. In this whole game, what does it really suck to be? And the gerbils, of course. And this we turned, when we did this work, we turned predator facilitation. So it's where the predators are actually facilitating each other through the game of fear and stealth. So without understanding the game being played, you would think they're just competitors. And are you ready for this? As the group sitting here from Moffitt, so who are all the Moffitt people? So for you guys from the Moffitt, that is where double-bind therapy comes from. This is actually, if you've heard of double-bind therapy, that was my very first cancer paper, is how could you create a therapeutic double-bind. Okay, well now let's go to a more interesting system, is snow leopards. So 2 of my grad students said they wanted to work with snow leopards. And my reaction when they said they wanted to work with snow leopards was, oh shit, I don't want to work with snow leopards. Not that there's, excuse the language, I'm sorry, that was, at any rate, well, I guess we're all adults in here, whatnot. But no, that was my reaction because, of course, it's great. Up there, this is Annapurna. For those who like mountains, you're staring at Annapurna 2 from the backside on there. But my reason for not wanting to, not that I don't think snow leopards are great. I've worked with mountain lions. I've worked with other big cats. But the problem is really awesome ecologists, much better mud and boots ecologists than me, have gone to these mountains. And they try to study snow leopards. And of course, we don't do that great at 4,000 meters. Snow leopards do really well at 4,000 meters, and they don't want to be seen. And they move much faster than you do at 4,000 meters. So these great ecologists go up there, they do a bunch of field seasons, they may or may not ever see a snow leopard, and they come back and they write a book titled Snow Leopards about how they survived and discovered inner peace. And so for me, the challenge was I'm not as good at running around the mountains as these great ecologists. And 2, my personality is so shallow, I wouldn't recognize inner peace if it hit me on the head. So it was what to do. So these are the 2 grad students. They're both amazing mud and boots ecologists. This guy is actually a department chair at Truman University. This guy, Soma Lee, actually has my position that I had at the University of Illinois at Chicago. Super proud of both of them. So the goal was, we became the first snow leopard project whose goal was to see no snow leopards. They don't want to be seen. So why bother? Instead, in the Annapurna, those are their prey, the blue sheep. Now, several things you'll notice, they're not blue. I have no idea why they got named blue sheep. It may be the elevation of the scientist that was watching them. The second thing about them, they're not sheep. They're actually in the goat family. But despite the fact that they have color problems and that they're taxonomically conflicted, this is the principal prey of the snow leopard in the Annapurna. And the idea was, they probably know everything we want to know about the snow leopards, because snow leopards are trying to find them. They probably have had aunts and uncles, sibs, that have been eaten by snow leopards. Is that going to make sense? Yeah. So we just need to download their data. And so the project was really fun. It did involve a lot of walking and whatnot. So to get to our study site, you did have to go over one of the 10 highest mountain passes in the world, 5,500 meters, as we tromp up to it. And at 5,500 meters, everybody's getting altitude sickness, but me, I can't help it. I love to turn to the Americans on the field team and say, you know what, where we're standing right now, as you're at the Turing Law, is the mile-high city of Denver, is 2 miles under your feet. Take that, Denver. And then here is a view from my tent when we're doing field work. The field work, and also it's not just snow leopards, a lot of our work, which is important to me when I'm working in these types of countries, speaking of game theory, is community development. So a lot of it is working with the local community, and the local community then helps us run our camp and whatnot. But the basic work was go find blue sheep, and they were easy to find. You find a bunch of blue sheep, and what do you notice about these blue sheep? Well, yeah, no. But what do you notice about these guys? They're kind of in a group, so herd size. So if there's more and more fear, you expect bigger herds than smaller herds, right? So that's one. Habitat choice. Are you in a habitat that's really easy for a snow leopard to catch you, or are you in a habitat that's harder for a snow leopard? And then the other, are you being vigilant? Are you being vigilant? And how would you describe these blue sheep? They're just not vigilant at all. And in fact, a couple of things I can tell you. One is this is actually a small herd. This is the kind of habitat that a snow leopard would die for, to catch a blue sheep. and these blue sheep are not being vigilant. This is an area that has not had snow leopards in years. In years. And if you go to an area that does get snow leopards in the area, they will be in herds of 50, 100. They will be in a very different landscape, and boy, heads up. Heads up, being vigilant. So we were able to show in the course of the project, yes, there were obviously snow leopards around. This is not taken from one of those vampire shows. That actually is the kill of a snow leopard on a blue sheep. But we were able to show that if you were willing in the Annapurna to sit and watch for 45 minutes, all you had to do, if you were willing to watch blue sheep for 45 minutes, you could tell with 95% confidence that this is an area that just doesn't get blue sheep, snow leopards, or this is an area that occasionally gets snow leopards. And if you're willing to watch for 90 minutes in an area where there's snow leopards, where there are snow leopards, you can tell with like 90% certainty, is the snow leopard in your valley right now? Or is a snow leopard wandering around somewhere else? All we had to do was download the data. So our goal was to basically find the shadow of the snow leopard and the behavior of the prey. The project worked. Mahesh got a job. That was great. So my lead district officer said, wow, this works. This is cool. So he wanted to do his PhD. So now we're in the Everest range. That's Mount Everest in the background. Instead of blue sheep, isn't that cool? That's a Himalayan tar. They kind of look like a cross between a Wookiee and a goat. But the cool thing is this is the principal prey of the snow leopards in the Everest range. By doing the same approach, we were able to count the snow leopards of the Everest range. But then, Somali, I'm sorry, am I doing okay? Am I totally blowing it?
You were good. If you want to wrap in 15, 20
You bet, absolutely. Is that okay with you guys? Yeah, that. So in this case then, what happened is Som got so good at reading the behavior of the prey. Guess what he started finding? He actually started finding the snow leopards themselves. So on one of my last field seasons in the Everest range, this guy, we just could see. We just used the Himalayan tar to triangulate. By spotting scope, triangulate, we knew there was a snow leopard somewhere. We found it. This guy, which is great, to the people in this area, these are the dogs of the gods. They know they're there, but nobody sees them. Nobody sees them. Even the villagers have never seen a snow leopard. They know they're there. They kill their yak. Sometimes they kill their livestock, but they've never seen them. And so we were able to get this guy, and this guy was great because as we kind of walked up, it was feeding on a blue sheep. And instead, it just gave us this look like cats do. You can't see me. You can't see me. And so this shot was taken from about 30 feet. And it just lay there and just flapped its tail back and forth and whatnot. And this in a series of photos for my grad student was worth about $70,000 of research money. So at any rate, Somali, I'm so proud of him, is he has probably now seen more snow leopards actually by eye in the wild than anybody on this planet. And if you think about it, if you're 1 in a million, there's 1,300 just like you in India. But he's 1 in 8.6 billion. How's that for cool? You know, how many of us can say something like that? Okay, so game theory and cancer. How does this then relate to cancer? How does this have anything to do? First off, as the Moffitt group knows, cancer would be easy to treat if it didn't evolve resistance. The evolution of resistance treatment failure is the primary cause of death, or is associated with death in most cancer patients. And in fact, it's because treating cancer is a game. It's a predator-prey game. In fact, when you apply therapy, if it's stage 1, stage 2, stage 3 cancer, in general, they can cure it. You kill them all. And if you kill them all, of course, then there's nothing left to treat. But guess what? If you don't kill them all, what do you suppose happens?
Proliferation.
They evolve first. First they evolve. There's that period of remission. Then they evolve resistance, and they proliferate. And then what you're left with was worse than what you began with. Does that kind of make sense? And so one of the messages, which is really interesting in cancer, is wittingly or unwittingly, the cancer therapist engage in an evolutionary game with the cancer cell. As soon as therapy is applied, it's game on. And the stakes is the life of a human being. How's that for high stakes in this case? The second observation, Cancer cells are what we call teleonomic. The cancer cells can only respond to what is currently happening or what has happened. The cancer cells have no way of sharing notes. They're saying, watch out. They're going to give you tamoxifen and it's horrible. We all died, but here's a note in a bottle. We did have a strategy, but we blew it, sort of thing. And so that's our biggest advantage, whereas the cancer therapy can be teleologic. It can plan in advance. This is actually called the leader-follower game. I'm going to say a little bit about it. So our whole, this table over here, which is really exciting, we get paid to imagine how you can anticipate and steer. How can you anticipate and steer? How can you engage the cancer in a chess match? And of course I have to, my favorite animal is squirrels. So it's a bit like squirrel hunting as a game. And you can imagine basically dogs versus coyotes. Dogs, if they're kind of just ordinary dogs, now some of you may have really smart dogs, but ordinary dogs, when they're chasing squirrels, they point right at the squirrel, they chase the squirrel, and of course what does the squirrel do? Runs up a tree, right? And the dog does this wide arc as it keeps pointing at the squirrel. Now if the dog is fast enough and the squirrel is far enough from a tree, it doesn't matter. The dog catches the squirrel, but most of the time the squirrel makes it to a tree. What do you suppose a clever coyote does?
Goes to the tree.
It cuts it off. The coyote anticipates where the squirrel is going to go and then cuts it off. Does that kind of make sense? Sometimes clever dogs will do that as well. Right now, in cancer therapy, you hear the ads for Moffitt, you hear the ads for all, Tampa General, all of them. What we do is we measure right down to the nanometer where your family member's cancer is. And we find the perfect therapy for where their cancer is. And then we blow that spot up until it doesn't work anymore. And after leaving a big toxic hole in the person, if there's a dead squirrel at the bottom of it, we did it. But guess what most of the time? The squirrel hasn't been there for a while. It's gone some. So we start as the leader and then we become the follower. And you see that all the time with late-stage cancers. Any of you that have had family members, friends that have died of late-stage cancer, you probably know the story. They were diagnosed. They were then given a therapy that was just great for where it was. You get a response, they go into remission. And then it comes roaring back. And when it comes roaring back, now you chase it. We do a second-line therapy, a third-line therapy. This is what we're trying to do. So this group from Moffitt is, can we anticipate and steer rather than chase it? Does that kind of make sense? So the first opportunity to do that was Jingsong Zhang. I won't go into a lot of detail on this, but Bob Gatenby, our thought leader, at that time Jessica Cunningham, was our math modeler. Jingsong Zhang was willing to try this in late-stage prostate cancer. So late-stage prostate cancer. And the idea that Bob had was that if you do maximum tolerable dose, which is the standard therapy, you simply select for resistance. You get a great response, but over time you wind up with resistance, and then you can't do anything. So the idea is maybe you shouldn't kill all the sensitive cells. How's this for a wild idea? Maybe leave some of the sensitive cells around, and then they become therapy through competition, call it competitive release, they become competition for the resistant cells. A crazy idea. Bob and a team of people verified it could work in mice, but it had never been verified in people. Jingsong Zhang was willing to give it a crack. He was willing to give it a try. And then I was brought in to do the modeling and a game theory model. In these, you have these sort of 3 cancer cell types in prostate cancer, and this is the late-stage prostate cancer. This is a patient. Everywhere it's black except for the bladder and a little bit around the jaw, that cancer burden. The chances and the opportunities for this patient is horrible. You're at kind of a last-ditch situation. But you have these cancer cells, not so important right now, but that need testosterone. They need external testosterone to divide. You got these guys that are really rude. They produce a public good. Remember our public good? They evolved to produce testosterone. How's that for rude? And then the T-minus evolved to be independent of testosterone. In the details of the model, got to write a model for it. It's basically, believe it or not, a variant of a rock, scissors, paper game. A rock, scissors, paper game, but that gives you a unique opportunity to kind of play with it. And so in this clinical trial, it was a very simple rule of thumb. Rather than trying to drive the cancer as low as possible, drive the cancer down using biomarkers of the disease burden to about half its level, and then stop therapy. Let the cancer come back. How's that for wild? And then when it gets back to another level, apply therapy again and knock it down. So for the patients that went into this trial, it was very courageous of them, because you're basically telling them, we're going to stop therapy when we know it's still working. How's that for weird? We're going to stop therapy before we know it is ineffective. And then we are going to welcome your tumor coming back. And then we're going to watch and watch. Remember that line of watch for the whites of their eyes on there? And so it was very courageous of Jingson to give it a try on there. It worked. Again, it's a late stage. We had 16. It's called adaptive therapy. That's the blue ones. 15 contemporaneous control. The numbers to watch here is median overall survival was 31 months for the control group. They're all dead as we speak. And then in the adaptive therapy component, it was 53 months. And 2 of these guys are still alive 11 years later. At any rate, what did this do? It unleashed what is now known as evolutionary therapies, which is great. There's now other clinical trials. This was started back in 2014. It's really wonderful to sort of see this is taking on as an opportunity to use ecology and evolution, mathematics, and try to steer. And it got me a job at Moffitt. Okay, so now, what if humans? Unless you're a hermit, we play a lot of games. We play a lot of games. How many people have noted the game of driving on I-75 or I-275? How many of you have noticed there's several strategies? One is, have you seen the strategy called the lane changers? Yeah. Always trying to get an edge. Do we have any lane changers here? No. Okay, there we go. Excellent. Yep, that's okay. And then have you seen there's the lane holders? I don't know if I'm in the best lane. But I just don't really want to be bothered with the stress of trying to change lanes. So who are lane holders here? Do we have any kind of like lane holders here? Until you discover there's a stalled vehicle in that lane. That. And then it's like, oh, darn. Okay, then there's the other strategy you notice on 275, coming at least from Moffitt and coming to like the airport. And that is you notice nobody drives the speed limit. You either have the group that's driving like 75, or you have the people from the lakes. I'm sorry, the old people. And they're all driving 10 miles below. They're all driving 10 miles below. Have you noticed your worst strategy is to drive the speed limit? Yeah, that's all. So you have to decide to kind of speed up or slow down. So who are the ones you just speed up? Go with the flow of traffic on there. How many of you slow down and get behind one of those persons that drives a big Lincoln Continental and looks like they're old? I'm sorry, and drives like 55 miles an hour. And you just get behind them. It's not my fault, guys. Not my fault. He's the one that's driving slow, and I'm just kind of driving behind them. So every day we play games. We play a massive number of games. Just the interactions in here. And the games take on many, many different forms. They can sometimes be nasty games. You say, please don't play games with me. Has anybody ever told you that? Don't toy with me. Don't play games with me on there. But on the other hand, no, most of the games we play are very, very cooperative. One game I love, which I think is great. How many of you have seen those sandhill cranes that just wander around fearlessly? And it's like really great. It's fun to see drivers, at least over by Moffitt. If you're a human being and you just start walking across Fletcher or Fowler, you're dead. Nobody's going to stop. But the moment a sandhill crane enters Fletcher, Fowler, everybody stops. It's like amazing. Yeah, it's like these drivers. Suddenly it's like, wow, it's a sandhill crane. And they'll sit there patiently. Some of them pull out their cell phone. The other game that I think is really fascinating, how many of you guys have noticed that the light cycles in Tampa are interminable?
Yes.
Have you seen that? You can read like War and Peace. In fact, the person in front of you is reading War and Peace. How many of you have had that circumstance where the light finally changes after 5 minutes and the person in front of you is just getting to the good part? It's just getting good here. You know that? And then how many of you noticed that encourages some people to run red lights? I'm driving, I know, crap. The light just turned yellow. If I stop, it's going to be 10 minutes of my life is going to be gone. And so they go shooting through. So what I'd like to do then is suggest a couple of things to very common words. These words, of course, have different kind of meanings, but these words are really useful for game theory. So naivete, actually, one way to define naivete is when you fail to see game theoretic intent where there's game theory. You fail to see you're being scammed. You fail to see that you're being led along. Oh, that do we have? Okay, do we have? Yeah, that.
I am.
So naivete, and that's always tough. So naivete can be defined as you're actually playing a game and you don't know it, and you only find out afterwards. It's like, oh crap! If I had only known now what I didn't know then, I wouldn't have been so naive. But the flip side of naivete is paranoia. And paranoia is imagining that everybody's out to get me. Paranoia is imagining that, oh my gosh, that every one of these is a game. Every one of these is a game when there is no game. Where there is no game theoretic intent. So interesting with humans, you can see it in these. So how many people in here consider themselves to be more naive than paranoid?
Me.
How many people in here consider themselves to be more paranoid than that? So what if humans? So I would like to leave you with a thought you probably have never ever heard in your life. This may be your first time. How many of you have read books on philosophy or what's the meaning of life or who are we as humans? You know, I think, therefore I am. And of course, how many of you have taken those wonderful anthropology courses? And there's the, you know, there's the robust Australopithecines. I haven't had any beer yet. And then there's the gracile guys. And then eventually you get Homo erectus and they start wandering around and brains get bigger and bigger and bigger. And of course, we're very proud of our big brains. But in fact, if you're a squirrel, you laugh at our big brains. Because several things are really odd about our big brains. One is, do we have a very good sense of smell compared to other animals? No. How about vision? How about hearing? No, which is kind of odd. And then our faces are flat, which means we have sinuses. We can get sinus headaches. Other ones don't. How many of you have problems remembering where you put your keys this morning? How many of you put something down, you don't know where you put it? A squirrel can remember where 1,000 things are buried. And I can't remember where I put my coffee cup. These guys know that, yeah. I can't remember where it is. How many also would agree that we're really terrible with facts? How many agree our president has problems with facts? His kind of fact challenged on there. How many agree that we're not really very good at facts? And what's also amazing, how many of you ever sat around and a friend or a colleague is telling a story of something and you were there? And you're like, I don't remember that on there. Yeah, that. And so what's really interesting then is, and of course, because we have big brains, we can get concussions. We can get strokes. So interestingly, if you think about our big brains, it's like, what the hell are they for? Yet we're so proud of them. We say that's what makes us really great. So here's what I'm going to suggest. There's an interesting class of games you put together. So there are what are called iterative games. And those are games you play over and over again. In fact, there are certain iterative games we play so many times you don't even think about it. Like driving. When you drive home, you're playing an iterative game. Walking across the street is an iterative game. Chatting with your neighbor is an iterative game. Trying to get something out of Sandy is an iterative game. Yeah, that you do on a variety of times. Let's see, what's going to be my best strategy this time with Sandy? Should I... Yeah. How do I catch them in a good mood? So often the games we play again and again and again. How many of you heard somebody say, I've learned from experience? Yeah. That's in response to iterative games. And of course, any of you, if you have parents, which I love it, and in game theories, anytime a parent comes up to you and says, I've learned from experience, what you should always say is, there's got to be a story. Anytime they say it, it means they screwed up somewhere. So that's your way is to turn the tables on your folks. When they say, look, I've learned from experience. Okay, tell me the story. How did you screw up? The other is what are called non-zero sum games. Non-zero sum games. And those are games that can be win-win or lose-lose. Your strategies, what you choose to do, can make the pie bigger or it can shrink the pie. Interestingly, Donald Trump generally frames all games as zero-sum. Have you noticed? He frames them as zero-sum. There's a winner, there's a loser. Iran will be crushed and we'll win. And if we don't crush Iran, they're going to nuke us tomorrow. Right? Have you heard kind of? And so zero-sum games, ironically, are easier to solve. Mathematically, zero-sum games are very easy to solve, actually. So framing things as a zero-sum games makes life easier, but you miss out on win-win and lose-lose opportunities. Social games means that most of our games are with the members of our own species. So unless you have a serious codependency problem with pigeons outside or with other things, but if you're a squirrel, some of your most important games at USF campus is getting food from the students. Either scaring the food from the students or finding students that'll feed you. Many of the squirrels' most important games in the day is not getting eaten by a hawk. So a lot of their games then are what we call interspecific. Whereas most of our games are social games. They're kind of among us, which is kind of cool. And then here's the kicker. They're games of imperfect information. So squirrels know what a squirrel wants. Have you ever heard that song, you know, what a girl wants, what a girl needs? Yeah. Now, if you substitute squirrel, it works. Substitute squirrel, it works. Boy, I can tell you what a squirrel wants and what a squirrel needs. It doesn't take much. It's not imperfect information. What you see is what you get. But humans, it's imperfect information. You never really know what. I can't really know what you're thinking. I can't know exactly how you're reacting to this incredibly long, boring presentation at this point that you're going, please, would this be over on there. And so it's imperfect information in the sense that we all have diverse motives. We all have diverse payoffs. We gain a sense of satisfaction in very, very diverse ways. So it's imperfect information. And in fact, what's great is, in fact, we are so much attuned to imperfect information that if I come up to Viral and say, you know what, Viral, I'm so glad to have you as a buddy, which I am. And I'm so glad I've had a chance to get to know you, and vice versa. That's great, right? But if I go to Viral and say, Viral, I understand you completely. I know you better than you know yourself. Viral's going, that's creepy. Yeah. You know, that's creepy. And if I'm right, Viral will change who he is to make sure it's no longer right. To make sure that it's no longer right. So in other words, what's interesting then is you're going to heard it here first. I think our big brains, and when I used to teach ecology and evolution, we get to the human ecology part and the human evolution part. I would argue our brains, what are they good for? Our brains are the most extreme adaptation for playing iterative, non-zero-sum social games of imperfect information, if you want to scribble it down. That's what I think it means to be human. We can play win-win games. They can also, every win-win game has an evil twin of being lose-lose. So what does it mean as a human? If you are a squirrel, what does it mean to be a good squirrel? Remember where you hide your nuts. Make sure you get nuts from other squirrels and they don't steal your nuts, and make sure you convince USF students to feed you. In the case of humans, maybe that's it. I think it'd be great if there's a God. I hope there is. I hope there's an afterlife. I really hope that all of these things we might imagine spiritually or whatnot. But at the end of the day, I don't know. I personally don't know. So what does it mean to live a good life? If you can say that most of your games were win-win and you avoided lose-lose, I would say that's a life well lived. And here's the kicker. Iterative game, non-zero-sum, iterative social games of imperfect information, they got a Nobel Prize for this, Arrow and Pratt. They have no solution. They have no solution. The joke's on us. The joke's on us. Evolution by natural selection has actually selected in humans, and probably no other species yet, a game that has no solution. I think that's pretty funny. Because as soon as you propose a solution, people will game it. The moment you write a book about how you can never lose on the stock market, it will, in fact, by the time they're writing the book, it's because it doesn't work anymore. Because if it still worked, guess what? They wouldn't tell you. Yeah, they would hide it. And so what's interesting is Arrow and Pratt were able to prove that this is the one class of games. There isn't a Nash solution. There isn't any. There's no Max-Min solution. That sucks. There's no group optimum. That really sucks. And there's no optimist. I'm feeling lucky. And there's no how can I screw my neighbor sort of strategy on here. And so I would say, yes, that this really describes what it is to be us. And I'll conclude with one of the nightmares I had. This is for the mathematician. So this has no solution. There's also a set of equations in mathematics. And in mathematics, these are called transcendental equations. Transcendental equations, if you've ever encountered them, they have a solution, but you can't solve for it. You can numerically solve for it, but you can't solve for it. There's no way to analytically separate the variables to get them. And so one of the worst nightmares I ever had is I dreamt I was a transcendental equation. Sitting on a sheet of paper looking out on the world. And I realized that I had a solution, but nobody would be able to solve me. Nobody would be able to kind of know me. And I woke up in a cold sweat. So, on there. So, please, thank you very much. Go out. May your games be win-win. Thank you guys for humoring me. As you can tell, it's a topic I love. I'll let you know one other secret. You'd think, and I remember when I was a faculty member, the department chair would come to me and say, oh my God, the upper administration is giving us hell. They're playing games with us. You're an expert game theorist. Could you please go figure out what they're doing? So I just want to remind you, all of us inherently are very good at playing social games. And guess what? It's like self-consciousness. The moment you learn game theory, you become terrible. Because you become self-conscious and you overthink it. And then it ruins your children. Because when your children know you play game theory and whatnot, you have your 11-year-old going when you're having an altercation. And your 11-year-old looks at you and goes, Dad, are you using game theory on me? Dad, you've already figured out what game we're playing. Are we playing the big pig, little pig game and whatnot? Anyway, yeah. So it also doesn't really help you when you're dealing with your children either. Anyway, happy to answer any questions, but I know there's kind of games to be had and beers to be drunk.
Yeah. I have a question. You say that the food came after competitive games between trees, but what do you think about Zanzibar saying that trees don't compete but they work together to get high?
Oh, so indeed there are a lot of mutualistic interactions, there's a lot of mutualisms, and those then become games in which you kind of elevate the competition to your group. So yes, between mycorrhizal fungi and whatnot, there are certainly examples then where the trees benefit.
From each other.
Yeah, from each other.
Only competition, yeah.
Right. But in general, the height of the tree has nothing to do with cooperation.
Okay.
Yeah, the height of that tree, it is just brutal competition for light, which is great. Because what it means is for us, it creates forests, it allows for tree squirrels. It does have all these amazing consequences, even though the game itself, you might say, is brutal. But without that game, you wouldn't have these magnificent forest habitats and whatnot. So yes, there's a huge amount of really interesting kind of games and whatnot that go on in nature. Thank you for asking that, and thank you for pointing that out. Absolutely. I didn't want to give that sort of nature red in tooth and claw. No, nature is much more subtle.
I had something, maybe some others can think about a question too, because I have think when I heard about the accelerometer tournaments, so I was super obsessed with it just because at the time I was actually trying to also combine the social behavior with genetics in a way. And then when you have a code based on game theory, and that can be in fact, again, encoded in the genome as well. And actually I think we have that sort of, and all of the maybe examples have one way or another, just they have the behavior. Now, from that perspective, and especially at the end, you were saying, there is no maybe perfect strategy, but there were really favorable, let's say, strategies. And what your inputs about it, like quartet, for example.
Oh, so if you have iterative non-zero-sum social games, there are solutions. If you have zero-sum social games of imperfect information, they're solvable. Just about any combination of these four things up there are solvable. But as soon as you have all four of those, that is not solvable. Then it's not. And so in most of nature, they haven't reached this point of the games that we tend to play. And this describes probably the most important games in our lives fall into this category. Whereas if you talk to a squirrel, it'd be like, no, your lives are complicated. My life's a lot simpler. Yeah, and the same thing for cancer cells. In theory, cancer cells are knowable if we can just figure them out. So cancer cells don't play the full suite. They do not play social games of imperfect information with each other. So no, so your point is well taken. That most of these other games, absolutely, they've been well worked out. They've been worked out in game theory. And it's exciting. It's fun taking these games and trying to find general solutions. But I'll also come out, if anybody has their kind of inner modeler or mathematician, a lot of the major problems in the mathematics of game theory have not been resolved. So there's gobs that can be done. The tracks are being laid even as people are applying the game theory. And new stuff is going on all the time. In fact, Viral and I will be heading off this summer to Istanbul to the meetings of the International Society of Dynamical Games. How's that for about as nerdy as you can get? Yeah, that. But game theory is now applied in military sciences, social sciences, lawyers have game theoretic algorithms, engineers designing airplanes, all across the board. There are game theorists employed in all sorts of different avenues of life. Okay, thank you all very, very much.